So let's take a look at genetic inheritance part 2. As we said last time, you get your traits from your mother and your father, but they have 2 traits between them and you have to have just one. As we saw, alleles that Gregor Mendel discovered mean that it is possible for 2 pieces of information to show just one trait, and Mendel also showed that this happens in real organisms, the pea plants that he studied. So we looked at how the genotypes, or the alleles, can show phenotypes in the real world, or traits. In this we're going to have a look at some combinations of real people and the kind of children they might produce in terms of one genetic trait. And we're going to start to think a little bit about probability to do this. So Mendelian traits are traits which obey the laws of Mendelian inheritance. So we know that Mendel discovered genetic traits that were easy to identify because they work by changing only one gene. And indeed, Mendel thought there was only one pair of alleles for each trait. Today we know that that is not true, and most traits need several or many different genes working together, and this makes them much more complicated to study. We do know of a few traits which do work from just one gene, and these are called Mendelian traits. And an example of this in humans is lactase persistence. So what is lactase persistence? Well, in most humans, the need to drink milk after they stop breastfeeding is very much reduced. So in most humans, we are genetically programmed to switch off the enzyme lactase after we stop breastfeeding. And that means we no longer have the enzyme that helps us to digest milk and other dairy products. But in places where humans drink milk from animals, there's been a recent evolution in those parts of the population. So in Central Europe, around 7,500 years ago, we see a new genetic trait emerging that allowed lactase to be produced throughout adult life. And that meant that you could digest milk throughout adult life. So this gene would have started by some kind of mutation, but how did it get passed on? So let's have a think about that first ever person who could drink milk easily with no digestive problems. The mutation could have come from many places, but it was probably only on one of the genes that person had. So remember, each person has 2 sets of chromosomes. If the mutation was on chromosome 6, then chromosome 6 on the other side probably was not mutated in the same way. So this means the person had one gene that enabled lactase production, and we're going to call that capital L, and one gene that does not enable it. We're going to call that small l. So the gene that enables lactase production gives lactase persistence, and if that is capital L, then is it going to be dominant or recessive? And the gene for no lactase production is small l. Is that going to be dominant or recessive? So if you remember our last video, the gene for lactase persistence is going to be dominant, and the gene for no lactase production is going to be recessive. So here is our milk drinker with a capital L, small l genotype for the trait of drinking milk. And one day they fell in love with a non-milk drinker, a normal small l genotype like everyone else in the world at this time. So eventually they had 4 children together. And here they are, their 4 children, but the question is, what genotype are their children going to be? So we assume that each person has a 50% chance of passing on each allele they have to each child. And this has been borne out by experiment. So the milk drinker has a 50% chance of passing on their dominant milk drinking gene and a 50% chance of passing on their recessive non-milk drinking gene. And the non-milk drinker, of course, will pass on a recessive gene, but still has a 50% chance of passing on either one. So let's look at the combinations, shall we? So if we look at these genes and we call each one A, B, C or D, if the 50% rule holds, then each gene will be passed to 2 of the children on average. It's always possible that the same gene could be passed to 4 children or 8 or 16 in a row. 50% is only a chance. It could go one way every time. But on average, each gene will be passed on to 2 of the children, and that gives us 4 different combinations that we can make. AC, BC, AD, and BD. Obviously, you cannot have CD or AB because each parent must pass on at least one allele to each child. So these are the 4 different combinations that we have, and that leads us to one of 2 different genotypes. So in an average situation, each of the 4 children will get a different pair of genes, even if many of those genes are the same from the non-milk drinking parent. And remember, of course, not all situations are average. We are talking about probability here. So, eventually, there were enough milk drinkers that one day 2 people who were both milk drinkers had children together. So we're not going to think about how long this took, and we're not going to focus on how closely related these people were. We now know, of course, that it's a very bad idea for people who are too closely related to have children together. But ignoring all of that, we one day had 2 people who were big L, small l, coming together and having children. And if we do the same combination game, we will find that there are now 3 possible genotypes that we can find. So we recognize 2 of the genotypes, but the new one is a person with 2 dominant lactase persistent genes, a capital L person. So 2 of the genotypes have similar alleles, and 2 of the genotypes have different alleles. Can you remember what the words were that we called these in the previous video? The ones with the same alleles, capital L, and small l, are homozygous, and the ones with different alleles are heterozygous. So what can we say about the phenotype of these children? Well, we can say that 3 out of 4 of them are lactase persistent. Only one of them is not. Only one child will have problems with that delicious milkshake in later life. But of the 3 who are, 2 of them are carriers of the non-persistent version of the gene. So these people may have non-lactase persistent children, even though they are lactase persistent themselves. But we can be absolutely sure that the child with the capital L genotype will only have children who are lactase persistent, because they will always pass on a capital L gene to all of their children. The only way it wouldn't happen is by some other mutation, and that is extremely unlikely. So, Punnett squares, a way that was invented by a man called Punnett to analyze combinations of genetic alleles, and we can use them in various ways, but we're going to look at a simple one shown here, and this is the case with our first ever milk drinker. So Punnett squares work by cross-referencing the alleles of the father along the top and those of the mother down the left hand side. And here we can see that Dad was a non-milk drinker and Mum was Gwen, the incredible milk-drinking woman, the first person in the world who was able to drink this delicious beverage. So Dad, a non-milk drinker, will give only small l alleles to all his children. So we know that no matter which side of the diagram they're on, they will receive. So in both of the columns from Dad, a small l allele is passed on. But Mum can give either a capital L or a small l to her children. So along the top row we put a capital L, and along the bottom row we put a small l. And this way we know that we have combined all of the possible combinations of Mum and Dad's genes. And that's the only Punnett Square we'll do in this video, but you'll be pleased to know there's another chance to see them on Crash Course Heredity when John and Hank Green look at a Punnett Square about another one of the Mendelian traits in humans. But anyway, for now that's where we'll leave it, and I'll see you next time.